going to look at the attack surface, and we're going to start off with traditional security. The way you're used to looking at things normally is you have your corporate network, so the corporate headquarters, and then this might be a factory someplace. And you have your network here, you have a gateway, you have a firewall, you have a VPN connection, right? And the gateway to get into the other places that you have. And the idea has always been that you have network firewalls blocking questionable access to the network. The communications passes through manageable gateways. You have a small number of outward-facing interfaces, and the incoming connections and interfaces are armored so that you limit the attacker's ability to access your system. And you fortify those that still exist. And unfortunately, things have progressed, and there's a larger battlefield that you have to look at now. And why is the attack surface, as we're used to thinking of it, fiction now? And the points I'm going to make is, number one, you don't control the set of machines that connect to your network anymore. The hardware vendors don't control what's in the products that they sell you. The software vendors do not control what's in the products that they send you anymore. And no one controls internet routing. Internet routing just sends things wherever they happen to go at the moment. We'll start with who is on your network. And there's the retailer Target in the US. In December 2013, a breach was exposed, 40 million credit cards, the personal information of 70 million people. It cost them $18.5 million. And what happened was their vendor for the air conditioning and heating had been hacked, and they had an interface with Target for electronic billing and project management. The hackers were able to use the credentials that they got to get into the network, and once they were in the network, they were able to get to the point of sale devices and get all that. It's been estimated that there are more than 55,000 HVAC vendors that have access to companies for remote monitoring of information, all that. This includes, I was interested to see, that actually includes the Olympic Park in Sochi as one of the places where they think that it's not adequately secured against that type of access. And then if you look at the BACnet, the Building Automation Control System standard, it takes care of elevators, it takes care of building security systems, connections to the smart grid, your power meters, and all of those use the same protocol. So that means that if your building has elevators or a security system, there's another company that has access to that, and you typically don't have control of their network. Another issue is bring your own device, which are the employee devices, which are then also behind the firewalls and are frequently connected to the corporate wireless. And for a while, companies came up with policies to enforce certain BYOD security guidelines, but they stopped doing it because there were too many different devices, too many operating systems, an almost infinite number of apps, and it was too much for them to take care of. And then another issue is, since these were the employees' personal devices, and a lot of the employees were doing unsafe behavior at home, the IT people didn't really feel comfortable policing the private lives of all the employees. So, and generally it was too expensive, nobody cooperated, and they gave up. One alternative would be to ban mobile devices in the workplace, but one time I gave a presentation at an NSA facility, and talking with them, they're not allowed to have mobile phones in their workplace, and they found that that's a hindrance in hiring young people. So, you might be able to hire people over 50, but if you want to hire somebody in their 20s or 30s that's used to having the phone with them all the time, they're probably not going to work for you. So the basic point is who's on your network. So heating, air conditioning, power security, all of the Internet of Things are not that well secured, and they're not things that you're in charge of securing. If you buy a TV lately, it's hard to find one that isn't Internet enabled. There's all the employee devices and all the Internet of Things consumer devices that you might buy. Typically, the design of the Internet-enabled devices nowadays is not designed for security purposes. It's designed to exfiltrate the information of the people that buy it. So that's the way they're designed, is to get information from inside your network to outside. And it's hard to believe that you cannot really go without buying normal devices nowadays, and they're all leaks. Device security is typically maintained by non-experts, and I haven't even mentioned issues with the cloud and outsourcing of data processing to the cloud. So basically, you lost control of the people accessing your network years ago, and there's not really much that you can do about that anymore. Hardware, there have been a number of cases lately where this one is from Bloomberg Businessweek, and their story was that China, they found Amazon Web Services servers that were being shipped from China, and they had a chip inserted here. Easy to pick that out from the screen, and that was there to exfiltrate. Now, this is a controversial story. Amazon says it's not true. The U.S. intelligence services say it is true, but no one's really claiming that this is an impossible situation or that it's unlikely. One of the issues is the hardware supply chains involve multiple corporations, multiple countries, and there's very little, it's almost impossible to really control if something has been added in there. Implants are hard to detect with quality control, so that we don't just think that it's China spying on the U.S. The U.S. has also, the Snowden leaks showed NSA had been implanting devices in Cisco routers while they were being shipped to the clients. Other cases that are documented, Syria bought some radar from the U.S., and the radar mysteriously stopped working the day that Israel decided to attack a Syrian facility. It's assumed by a number of people that there was probably some sort of hardware implant that allowed a remote to be remotely disabled. Now, U.S. arms manufacturers claim that the French do the same thing with the arms that they sell, that they then put in the possibility to degrade the arms that they're selling to other people in case they should have some sort of conflict. Detection of hardware Trojans is a largely unsolved problem. It's very challenging. I have not had research in that area, but I've had research programs with other people that are working in that area. And in general, finding if somebody has inserted something into a chip where the chip is being fabricated in another country is a non-trivial problem, and outsourcing production has just made that worse. One thing that is possible that isn't really being done yet that we know of, but there's a professor in our department that does nanotech, and we've had discussions about what you could do to set up nanoscale Trojans. So it would be entirely possible to manufacture chips with features at the nanoscale level, which you could detect with an electron microscope. But you would really need to do that to be certain that nothing was added there. And those would be very hard to do. Another disturbing thing is hard disk drives, the solid state ones. Firmware has been found with malware inside of it. This is then invisible for scanning. It's almost indestructible. The current version was a cyber espionage group equation. The Kaspersky analysis called it rare as pandas walking across the street. However, what happens with security flaws like this, once it occurs and people know that it can occur, then it becomes more likely. And another problem is that frequently after you have attacks, the software or the technology becomes public record, and it becomes easier to replicate. There's also the Triton industrial control system malware, which put malware into the safety control system logic for industrial systems. And it was meant specifically to do high impact damage to industrial control systems, which is relevant to most of the people that are here. And okay, hardware attacks are rare now, but there have been a number of known attacks, primarily by nation states. And since industry, manufacturing, all the industrial systems are critical infrastructure, they are vulnerable. And one of the problems is that when nation states do this, the basic technology leaks, such as with Stuxnet and Flame. The software got out there, people saw what was done, and it became very easy to replicate it. And lower level attackers can reuse it. Okay, Kaspersky does sell UEFI antivirus. Now, UEFI are, in the computer, the hardware root of trust. So these are hardened chips that were developed to specifically verify the operating systems as part of a secure boot. And just the fact that people have succeeded in getting malware in there, and that you need to have something, or that somebody even bothered to produce something to scan a specially hardened security chip, should be worrisome, should have everyone concerned. Another issue is that, okay, with my security course, I had a hacker, ethical hacker come by, and he was talking about fuzzing, and they were attacking some of the software-defined networking in the latest version of the 802.11 chips. And we were talking, he was claiming it's because it used to be hard-coded, but now it's software. And the more I thought about it, the more that really didn't make sense to me, because if it's logic, then the fact that it's in bits or in silicon doesn't really make that much of a difference. And I then talked with a colleague who does hardware-based security, and we laughed about it, or he started laughing, because from his point of view, hardware is mainly firmware. It's largely reprogrammable, so it's not really more secure. From my point of view, I've gotten to be of the view that the issue is more that replacing hardware will cost the vendor money, so they make some effort to test it. You know, unlike software where it costs you nothing to put a patch up, so a patch online, so they do no testing. They let you do the testing in your facility. So there is some amount of testing, probably nowhere near enough testing, but there is some testing with the hardware, and that would make it slightly more secure. In terms of the software supply chain, Ken Thompson, in his Turing Award speech on trusting trust, came up with a story that may or may not be true. He said that they were thinking in the early days when they were building Unix, they thought it would be good to be able to fix all of the Unix systems. So he changed the login command so that he would have a backdoor to all of the systems where he'd have a username and password. Then he thought somebody could look at the software for the login command and see that. So he changed the code for the C compiler and then made it so that the C compiler would see if it was compiling the login command. And if so, it would insert the backdoor. So you couldn't find that in the login command anymore. And then he decided that he would use a normal compiler to compile that C compiler with clean source, so that there was a C compiler that would insert the so that the compiled C compiler would insert the backdoor in the login command. But even if you looked at the source code of everything, there would be nothing to see. And the basic proof is that you can insert malware with nothing bad in the source code going all the way back. And that's sort of the start, or one of the better explanations of supply chain attacks. And we've been seeing more of them. TeamViewer credentials were stolen from the company that was producing Crap Cleaner. And so Crap Cleaner software that was used to get rid of temporary files. And the ShadowPad attack was when a lot of different companies started using the infected Crap Cleaner, which then infected their software, which was then sent out. The ASUS laptop vendor Shadowhammer attack was an update that was pushed. So their development systems were infected. It's unclear, but it seems like they might have been infected with the Crap Cleaner thing. And they were then able to, or rather what happened was they created new updates to the BIOS and the UEFI, and those were pushed out to customers. And those were legitimate signed updates from the vendor. Up to 1 million machines were infected. They found that in the logic of the infection, it seemed that there were 600 specific machines where the attacker knew the MAC addresses that were then actually used to do malicious activities. So the security orthodoxy has always been keep your patches up to date. But if the patches are now a way of spreading malware, it's hard to say if that really is the right thing to do. Similar, NotPetya was spread the same way. The Havix attack on industrial control systems, the Juniper Network source code. There was a fake developer tool for iOS, Android, Python, JavaScript. All of these have had a poisoned supply chain. And according to NIST, this is now the new normal. So that the software vendors have no control anymore. And that is ignoring the shared objects and dynamic link libraries, which if you look at the standard malware reverse engineering text, it has 2 chapters built on DLLs and how you can use DLLs to hijack and insert malware behavior and then also launch your malware more covertly. It's become a standard way of inserting malware into processes. So, again, to go back, you don't really control the people that have access to your network because there are all sorts of other devices that are behind your firewalls. The hardware is somewhat trustworthy, but not near as trustworthy as you would like, including the hardware, the specially hardened hardware root of trust chips, which have also been attacked. And then the software vendors, supply chain attacks are the normal thing. And unfortunately, The network routing is not better. It's inherently insecure. This was from last week. There's a good webpage, bgpstream.com, that has a list of all the BGP incidents within the last, it has historical data, but basically the last 2 or 3 days will be enough to have a long listing, and there are also nice animations, which I'm not going to show you, but you can see them there. But again, look at how many incidents there are and how they're distributed. Again, this was just happened to be the day that I was doing it. And here's then BGP hijacking, which is taking traffic from a Russian site and sending it out someplace else. And the interdomain routing is totally insecure. Denial of service is trivial. It's very easy to just send the traffic off wherever you want. There have been large parts of Japan that have disappeared. YouTube was taken offline by Pakistan. And also the routing of traffic for surveillance is trivial. For example, China has enough points of presence for BGP in the US that it's just widely known that any US internet traffic can be routed through China for surveillance. Here's then an attack where Hong Kong traffic was then routed through Taiwan. And so again, the China points of presence can hijack the US traffic whenever they want. One of my things that I really liked was Nigerian Google traffic was routed through China and Russia, and it's hard to believe that the shortest route from Nigeria to Silicon Valley is through China and then Russia. And all of the Taiwanese DNS traffic have also been routed through Brazil. Okay, so those are the problems. There are some things that are happening that could be used in a positive way. For those of you that know the Onion Router Tor, they've been working on technology where you can produce identical binary builds on any system so that you can have totally divorced machines that do the same build, and then you can compare them, and if they're not the same, then you could use that for something to, then you could use that to try and track down. And so you can compare also your local build from the source to the downloads that there are. And this is a good idea for building in resistance to the software supply chain attacks. I just find it really strange that the crypto-anarchist community are the people that came up with this security measure rather than, say, the commercial vendors. Granted, they are more paranoid than the other people. Another thing that we can use that would be helpful, and okay, those who want to know the details of the math, you can come to me afterwards. I'm not going to go into too much detail. This is a solution of this particular game, this particular competition, and then encodes different possible moves from people. And what this is this is an expression of the possibility that you could be playing multiple games with somebody else at the same time. The math to find the best answer for something like that is p-space complete. For those of you who understand NP-complete, okay, an NP-complete is an optimization problem where you have to try all the possibilities to find the right answer. P-space complete is that squared pretty much. So you have to try all the possibilities of the one side and then try all the possibilities of the other side. Generally, NP-complete is considered intractable. This is much worse than that. So you can't find the best answer, but you can find an answer within a known constant distance of the best. and this works in linear time. So it is possible to find ways of prioritizing your reactions to the thing, because in essence, you're in a competition, multiple machines at multiple layers at the same time, and you're not going to be able to do everything at the same time. So it's possible to find good answers, not the best answer, but it would be worthwhile building strategy into the security systems. This is a project that we've been doing, which would look at, this would go against, say, some of the issues with BGP, where instead of, we're actually doing this on the live network, but instead of having like a fixed IP address for for the source and the destination, it's sort of like frequency hopping in radio. You use random IP addresses on both sides, and you both have to be able to get the same random sequence. But if you do that, and say every packet in a session has a totally different IP address for source and destination than other packets, it becomes much harder to do man in the middle, it becomes much harder to do hijacking, it becomes much harder to do surveillance because you can't really figure out what the sessions are. This is theory, but it would be a better way of doing it. Now, the other thing, which is a possible move forward, is using the blockchain. Now, if I'm going to talk about the blockchain, I want to start with a set of quotes from the most respected people in the... So Bruce Schneier says, the blockchain and cryptocurrencies are honestly useless. Noted economist Rubini says, blockchain is useless and they're all scams. Stinchcomb, blockchain is not only crappy technology, but a bad vision for the future. Blockchain is ridiculous and dangerous. And then one of my favorites, blockchain is a useless technology. I don't agree. What's interesting is, particularly, Ethereum has the idea of smart contracts, where it takes inputs from the distributed blockchain and you run the same program on multiple servers simultaneously, so that it's, if not impossible, it's difficult to forge the inputs, and it's then the case that, you know, if you were to infect one machine, there's not much you can do with that. There are a number of problems with the way it's currently implemented. It has to run in parallel on all of the machines all over the world, which is not the best idea. There'd be better ways of doing that. And also, for me personally, if I was designing a secure computational framework, I don't think I would have picked JavaScript as the implementation language. And the set of inputs that it can currently take are very restricted. However, the idea of having programs that run in parallel throughout the system and where you've secured the inputs to the programs is very interesting, and it could be very useful for getting around a lot of these problems, because then it's not the case that an intruder would just have to get into your system and infect and modify one machine, and then they can do whatever they want. They would have to take over 55% of your machines in order to change the results. And that totally changes the calculus involved. Again, we're not there right now for industrial systems, but it would be a useful direction to go with a number of the things. It would change and make it a lot more secure. So, summary, the attack surface, as we've been thinking about it, is no longer limited. The current electronics and the current way of doing business allows network access everywhere, and you're not really going to be able to restrict it that much. You know, because you're going to have some consumer devices in your network, and they're just designed to leak data. And you have vendors, you're going to have an elevator, everybody has their mobile phones. Hardware from vendors is no longer really secure. As I said, for the moment, this has been mainly nation states, but once the attacks become known, and if there's enough incentive, then it becomes more widely spread and easier. And then also, again, with the industrial systems, they're a part of the critical infrastructure of a country. It can become a target with a conflict between different nation states. That's not unrealistic. Supply chain attacks make all software everywhere vulnerable, and network paths go anywhere. There's no control over that. Possible solutions, the deterministic builds is a very good idea for getting rid of a lot of the supply chain attacks. Companies could start doing that and verifying things before they ship it. Network traffic obfuscation is another good way of avoiding some of the problems with traffic being hijacked and surveilled. Building strategic thinking into the security tools would also be a good idea, because they're not going to be able to do all the processing everywhere that they'd have to do, but then they could choose to make the moves that would be that make the most difference. And then smart contracts can create security from the distributed computer. So instead of having security, the idea of security always be that you have the machine in a physically secure space with minimal network connections, that's no longer realistic. But if you then have it so that the trust is largely distributed, so you don't get the trust from below, but you get it from the distribution of all your processing, that's probably the way things are going to have to go in the future. But you have to, it's not like the word blockchain is magic. You will need to have a certain amount of engineering and design and implementation to make anything like that work.